A warm welcome to Professor Srikanth sir from University of Hyderabad. Sir will give a lecture on overview of nanomaterials. Thank you, sir. You can just introduce
Yeah,
yourself. Yes.
yeah, okay. Yeah, thank you, madam. I'm, as you said, I'm Srikanth. I've been working at University of Hyderabad since 2009 December. I am a professor there, and our research team works on various aspects of nanomaterials, um, environmental applications, energy applications, and bio applications, and so on. Um, we, of course, we deal with varieties of materials in our team, but we basically concentrate on carbon nanomaterials. Most of them are carbon nanomaterials. And yeah, I am happy to see our team member here, Venkateswarlu, who is pursuing PhD at University of Hyderabad in my team. So the today I'll be introducing to you the way to understand nanomaterials, which many people who study nanomaterials miss. What I'll do is I'll take examples wherever possible, and then try to make you understand how nanomaterials should be perceived or understood. Okay, and my presentation will be rudimentary in nature, and before I give my presentation, I would like to strongly state that nanotechnology is by virtue of design. Okay, it is not when I say virtue by virtue of design, uh, it means that even before the experiment is done, one can scientifically anticipate the outcome of the result. I also mean that nanotechnology is not arbitrary in nature, and it does not involve any trial and error experiments. Okay, and for nanotechnology to be by virtue of design, understanding and controlling size are of utmost importance. So size matters a lot. The dimensions matter a lot, and we'll try to see through my presentation how this aspect of size, controlling size, and what is the significance of size is important in order to venture into nanoscience and nanotechnology. So let me start by explaining the word technology. I'm sure most of you are aware of this, but let me put it in a different perspective, or my perspective, so that we kickstart the presentation. Um, Technology is application of science to make our lives, most of us, I mean humans, lives comfortable than it was earlier. And of course, in doing so, we also take care of, as engineers and technologists, while making our lives comfortable, we should also see that the nature, the environment, is also safe, because we are not the only beings in the on the planet. There are other animals and plants uh, which are also very important. Technology basically constitutes tools. Here you can see the tools used by the early humans, or the machines like aero engines. The technology also constitutes manufacturing of drugs for different ailments. It also constitutes processes like reverse osmosis. You might have noticed that of late, many of the houses have this RO plants for drinking water in our in our day-to-day usage. Now this process also constitutes technology, and all of these, either tools or machines or drugs or processes, are developed based on some scientific principles. That is the core of technology, because otherwise there is no technology. Science is a robust set of rules and regulations which don't fail. And if we develop anything based on science, scientific principles, that technology also doesn't fail. That is the idea. So, but then what is science? Science is a testable explanation of any observation around us. We as humans are very curious. We observe various things around us, and we wish to give reasons or find reasons for those observations, what we observe around us. Science also constitutes testable predictions. You can also predict something without doing an experiment. You can also predict what can happen if you conduct an experiment. Okay, so you can also predict the outcome. Okay, that also constitutes science or the scientific principles. And of course, both of these, both the explanations or the reasons and the predictions are based on robust set of rules and formulae. And we are aware that we have physical laws of physics, for example, Newton's laws of gravitation, and so on, laws of chemistry, atomic and molecular interactions, compound formation, for example, home rules, diffusion, and so on. And then, in fact, there are also laws in biology. Cell division is not arbitrary. It follows a particular rule and regulation. Genetic code behaviors, protein folding and unfolding, all of these come under laws of biology. Now, this is most of us know all of these. We have been following different rules, fluid mechanics and Bernoulli's principle, so on and so forth. Strength of materials. You have, there is the Newton's laws of motion. All these are well established, well tested, and most of them are fundamental in nature, and some of them are empirical in nature. We have been using them. But then what is science at small scale? Okay, because we want to discuss about nanoscience and technology, that as we stated, that it is at a small length scale called nanoscale. We'll see what that is. But in order to understand that, we need to figure out what science at small length scale is. That is very important. So I'll try to explain this using one example, free fall of a body under gravity. Okay, now see, to understand, and we'll try to also correlate between the size and the observation, and the corresponding reasoning behind this observation. So for this, let us consider three bodies. Here, a stone, and a sheet of a paper, and an ant. Of course, we will not harm the ant in when it falls. It is just an imagination. And we can hold the stone in our hand, implying that its dimensions are of several centimeters. In the case of paper, the dimension along the thickness is several orders smaller in comparison to the dimensions in the other two directions of the paper. Of course, the dimensions in the other two directions of the paper, the length and the breadth, can be compared to the dimensions of the stone in several centimeters. Okay, and with whatever knowledge we have till now, let us imagine dropping these three bodies under gravity, under the same conditions, and observe them falling. In the case of stone, the standard Newton's laws of gravity are applicable to understand or to explain the fall of stone under gravity. But in the case of paper, our observation is different, would be different. It is not falling, it will not fall the way the stone falls, isn't it? And you have to now, the rule, the gravitation law that explains the fall of stone under gravity is no more applicable to explain the fall of a paper under gravity, because here you have to bring in buoyancy into the picture in order to understand or to explain the observation, which is the fall of paper under gravity. Now, as the paper falls due to gravity, an upward force, that is a buoyancy, acts on it due to its large surface area, which is owing to the reduced dimension in the thickness direction. Okay, so if it had also the similar dimensions, if the paper had the similar dimensions which it has in the other two directions, along the thickness direction, if it has the same then it is again a big object, okay, a massive object, a macro object. Therefore we don't talk about buoyancy there. It is more or less like a stone. Okay, so this is the difference. There is a difference in observation, and in order to explain that observation, we are curious why paper is not falling like a stone. So therefore we need to study, we need to do set up experiments, we need to understand. We develop science which we say buoyancy. Okay, that buoyancy is critical in explaining the fall of paper under gravity. In the case of ant too, the standard laws, either the laws that are used to explain the stone of the fall of stone or the fall of a paper are not applicable. Buoyancy won't be applicable here. In this case, when the ant is falling, okay, the third object, the ant is falling, the viscosity of the medium plays an important role. Here, the terminal velocity, the Stokes law, uh, you might be using them in fluid mechanics, in mechanical engineering. Have to be used. These have to be used. Terminal velocity, Stokes law have to be used to explain or to understand the observation of fall of ant under gravity. Now, please keep in mind that the acceleration due to gravity in all these cases is the same. Okay, it is only the rate at which each of these bodies are falling under the gravity is different. That is the core observation. So, in this particular example. Now, it is very important now, as we see that even with the known examples, we have not tried to understand by combining these three examples together for quite some time. Okay, we never thought of comparing these and we never thought that these will be useful in understanding the size dependent science. This example is a classical example of science dependent science. The problem is fall of body under gravity, but the moment we change the dimensions of the bodies, the observation changed and the reasoning behind the observations changed. Now, if we consider further another body, let us hypothetically assume a hydrogen or a nitrogen molecule in a dropping of a nitrogen molecule in the same environment. Now, in that case, nitrogen molecule in all x, y, z directions, the dimensions are considerably smaller than these three objects put on the slide: stone, paper, and ant, isn't it? So now, if you consider nitrogen molecule and drop it the way you dropped stone, paper, and ant, the laws that are helpful in explaining the fall of stone, the law of buoyancy in explaining the fall of paper, or the Stokes law useful in explaining ant, are not applicable in the case of nitrogen molecule, because again here the dimensions are so small. So the observation, so imagine you're dropping a nitrogen molecule in a room, in the room conditions. Under the room conditions, you have turbulence. The air molecules are turbulently moving here and there with great speeds, and therefore these particles will be hitting this nitrogen molecule from all sides, and then will not allow the nitrogen molecule to fall so easily against the gravity, right? So now in that case, unless you bring in the concept of turbulence and the rules and regulations or the laws or the formulae related to turbulence, you will not be able to explain the fall of nitrogen under gravity. So if you see here, the moment the size changed, and even when the problem is fall of body under gravity, if the size changes, your observation changes, and the reasoning behind the observation changes. Okay, now that we have established the correlation between science and observation and the reasoning behind the observation, let us try to understand nanotechnology and nanoscience. Okay, nanotechnology is basically a miniaturized technology that is based on the science called nanoscience. Okay. Now, if we let us consider an example of a data storage or reading devices. For example, USB stick. USB stick is a very small device, and within that device there'll be very small chips kind of arrangement, some circuits and all that, which help to store data, read data, write data, erase data, and again rewrite the data. Now, this is an example of miniaturized technology. And what I am trying to say is this technology is not based on the regular science called um, the regular science, the classical science we know, but it is based on a science called nanoscience. Okay, if not for the phenomenon called Jaint magnetoresistance. Okay, some of you might be knowing GMR effect. This data storage, what example I've taken, is not possible. Okay, data reading is not possible, data writing is not possible, and this whole technology would not have been possible. Now, this phenomenon, this science, this phenomenon called Jaint magnetoresistance is a nanomagnetic phenomenon which involves, electron scattering based on electron spin in a nanosystem constituted by three layers made up of iron, chromium, and iron. Okay. Now, in order to develop this technology, first you need to make the nanomaterial. Okay, so but what is the basis on which you make this nanomaterial? How do you know that it will work? So a lot of theoretical work would have gone into this in designing the nano system, and this particular GMR effect is by virtue of design. Okay, so because why I'm saying this is because the scientists Peter Grunberg and Albert Fred knew the correlation, already knew the correlation between the dimensions and the scattering length of electrons in iron and chromium. So that is a discussion with which I want to bring all of you onto this slide. So the only bottleneck was the preparation of the nano system. Okay, so they already knew, the scientists knew what is scattering length of electrons in iron and chromium, and what is its correlation with the size of the layer iron, chromium, or iron, what they wanted to prepare. Okay, and once the moment they prepared and measured whatever they hypothesized, that came out perfectly correct, and they won the Nobel Prize, and of course they have been enjoying the benefits of it. Now, if let me, I think I should have one example somewhere, but I think I missed it. Okay, yeah. Okay, anyhow, if not for these USB sticks, small USB sticks, and which store lots of data, in small areas, but they store terabytes of data. If not for the GMR effect, this is not possible. Huh? In 1956, IBM prepared the first data storage device, which was about 16 square feet in dimension. Okay, 16 square feet and weighed about 100 kilograms. A huge structure which they called as a data storage device. Huge structure, 100 kilogram structure, and can you imagine how much data it can be, that device could store? The device could store only one D800 raw file. You know what is D800 raw file? It just occupies about 40 to 70 MB space. D800 raw file is the raw file that is generated when you click a photograph using your mobile phone. Okay, of course the photograph that you see is a processed image, but the raw file that is generated in the processor inside your mobile is called as a D800 raw file. And in 1956, a device which is 100 kilograms in weight and about 16 square feet in dimensions was used in developing in storing just one 800 D800 raw file. And from there it took almost 30 years, because GMR effect was invented in 1988. Okay, and from 1988 it took further more years to develop the technology. Science was established, but how to make a device and so on. And from late 90s, these devices started coming up, floppy disk, and then and to store the data. And then we know the compact disk, CDs, right? CDs, we have been using those CDs, and now from CDs to we have USB devices where we put a lot of data into them. So all of this is possible because of this GMR effect. Okay, so let me I think just a minute. Just give me a minute. I think I've shared a wrong file, but I just want to share the correct one and then continue. Yeah. Am I audible? Is it visible, the slide?
Yes, sir.
Yes, sir.
Yeah. Okay. So here you see the example I've been talking about. This is the device that can store only one D800 raw file, and you see that these are 6 feet tall persons, and 100 kilograms in weight, and this can only store just one file. Okay, so imagine if you want to store 1,000 photographs in your phone, you might need 1,000 such huge devices to store the data way back in 1956. Okay, so from this stage we have and this is all dependent on the Jaint magneto resistance that I was talking about, where the electron scattering dependent spin orientation, this is the new phenomenon. The moment you have this structure, nanostructure, like a few nanometers of iron and few nanometers of chromium and few nanometers of iron, the way the electron gets scattered, the electron gets scattered across across this structure can be controlled, like 0 1 0 1. Okay, so if the spins in both iron and iron layers are parallel, the resistance is very low to the electron scattering, therefore the electron won't scatter. Okay, resistance is low, that means that it will scatter very easily. But if the spins in iron and iron are opposite to each other, the resistance is high and the electron is unable to scatter. That is a zero condition, one condition and zero condition, as we know in electronics. So this has been used to store bits of data. Okay, so this without this our devices, storage devices, in computers or reading, writing, calculating, all this would not have been possible. This is how this changed our lifestyle and the way we got benefited from this science. Okay, and of course the related technology. Now these are the devices which we have been using: small devices, disks, and reading devices and storage devices and calculating, rams. We have developed so many efficient rams and all that. Now is nano new? No, definitely not new. It is only the terminology that is new. If you see in on this slide, we have taken three examples: one in biology, one in chemistry, and one in physics. In biology, even before the advent of the word nano, people, scientists have been dealing with DNA. For example, DNA studies, the structure of DNA itself, elucidating the structure of DNA itself won the Nobel Prize. And it is there, people have been dealing with DNA for a long time. The same is with a molecule called polypyrrole, which is a well known organic light emitting diode material. Again, we have been using this for quite some time, even before the advent of the word nano. In physics, people have been dealing with the quantum mechanics, which actually deals with small systems, ultra small and ultra small systems. So in for a long time, until the word nanoscience, nanotechnology was brought into the picture. We as the scientists and humans who are working in science have been using the units, angstrom units. Okay, but subsequently, if you remember, in our school books also, we used to read that the visible wavelength region is 4,000 to 7,000 angstrom units. But now they've changed the units all over the world. They are now saying 400 to 700 nanometers. But it doesn't mean that we didn't know about the wavelength of the light before. Okay, similarly with this DNA and chemistry and physics, we have been dealing with several objects and systems which are quite small. Okay, and but then how old is nano? Okay, so if we see this example, here is a bacterium called Magneto bacterium, which is very it has been living on this planet for 2 billion years altogether, from the moment the life started on this planet, and this has been living on this planet. And if you see here, this particular bacterium has a very nice arrangement of specific magnetic particles, Fe3O4 nanoparticles. Okay, magnetite nanoparticles, specific in number, specific in size, neatly arranged in a polymeric package, and they are in the bacteria. Okay, and what is the advantage? What is the technology you're talking about? Okay, who put it? It's actually the nature has put them in the bacteria. And these small magnets, spherical magnets, are acting like a bar magnet, helping the bacterium align with the Earth's magnetic field, and trying to tell the bacterium, which requires oxygen as its food, where the more oxygen concentration is there on this planet. If you know, in one of the poles, North Pole or South Pole, I don't exactly remember, the oxygen concentration is more. So how does this bacteria know that oxygen concentration is more somewhere? It has to align along the Earth's magnetic field. Okay, and these magnets, small magnets which are there inside the bacterium, have been helping the bacterium in finding its food. And not only that, these nanoparticles which are there are classified as magnetosomes. As the bacteria breaks into offsprings, these magnetosomes are transferred to the next generation. Okay, so this is a very old nano is very old. It is not new for the environment. It is only for the humans. We started and made it popular and trying to hype a lot of things in the recent past. Okay, so so when somebody asks what is how old is nano, you can comfortably say as old as the life started on this planet. Okay, similar examples are there. If you see chloroplast, which is helpful in preparing food, plants prepare food through photosynthesis. In chloroplast, if you see, there are important constituents called thylakoids. These are the thylakoids. This is a schematic and this is a real image. Are you able to see when I'm writing?
Yes, sir. We can see.
Anybody?
We can
Yeah,
see, sir.
okay. So these are these are the schematics. These are the schematics, but this is the real image, thylakoids. And if you see the dimensions of the thylakoids, again they are in the nano scale. Okay, and surprisingly, the outer membrane of the chloroplast, the thickness of the membrane of the chloroplast is exactly 1 nanometer. But what is the importance of this? Why it is only 1 nanometer? Why not 2 nanometers or 10 nanometers? So uh, with whatever limited knowledge the humans have till now, they can only say if it is not 1 nanometer, chloroplast would not have been stable. That is again through they cannot do any experiments to prove it, but they can simulate, model and simulate and then try to find out and only explain in terms of the stability. Okay, so you will see such examples where why is it important for humans? Through photosynthesis, the plants, all the plants together put on the planet produce about 300 quadrillion. Quadrillion is 10 power more than 10 power 20. Okay, 300 multiplied by 10 power 20 sugar cubes per year. So imagine sugar is food, energy. So imagine replicating at least 1% of photosynthesis artificially. The people, scientists are working, but still there is no big success in artificial photosynthesis. Okay, and if we can replicate this, we can solve the food problem in the world. Similar example you can cite is a ribosome. It's a nano machine. Ribosome, without ribosome, the continuation of human life is not possible, because ribosome is a machine that makes the proteins, and nobody tells it ribosome inside our body what protein should be made and how to make it, but it knows what protein is needed for the body and what amino acids it has to collect and make the protein, and it does at a very high frequency of 99.9%. And again, the interesting thing is its dimensions. Again, this is the schematic. The dimensions are again in the nanometer region. Okay, and this is the real image. This is the real image, and this is the schematic. Okay, and from when the ribosome is there, the moment the life has started and the humans have started living, ribosome is there and it is helping us. It is again a nano machine. So is nano new? Definitely not. Another example is the human brain. You have 100 billion neurons. Each one is having 1,000 connections, and if you see the dimensions of them is again falling in the nanometer scale. Okay, and what is the importance here? A single operation by the brain, single operation, just you can think anything in your mind, that just takes about 10 power minus 15 joules of your energy, which is nothing. Okay, so imagine replicating the neurons and the connections between these neurons and try to make a computer. Okay, that is what people are doing by combining artificial neural network, machine learning and human knowledge, whatever knowledge, the brain knowledge people have in developing computing, efficient computing, So because why? Because the energy that is used for such computing will be very less, because as they calculated here, for a single operation in human brain, just a single thought just takes about 10 power minus 15 joules. So again, this is also not new. We knew it long before. Okay, now what is important for nanotechnology is nanomaterials. Okay, like in nature, materials are important. You have seen in the case of bacterium, the spherical nanoparticles are important. Similarly, in any device you want to make, and any new technology called nanotechnology you want to make, based on some science called nanoscience, you need nanomaterials. And nanomaterials derive their special properties from having one or more dimensions compared to a length scale critical to the science behind in the phenomenon. Okay, let us try to understand this through an example of a copper material. Okay, let me take you there directly. Okay, understanding nanoscience. Okay, I have two pieces of materials. One is a bulk copper, a piece. I mean, imagine a metal piece of copper is put in your hand, and another piece of similar dimensions, the outer dimensions, same weight, everything is the same, is put again in another hand. Okay, you have two pieces of copper, but one is called as bulk copper and the other one is called as nanocrystalline copper. We don't need to bother about why nano and all that. Let us try to, both are made up of copper atoms, but in one case the size of the grains is very big. In the other case, the size of the average size of the grains, copper grains, is just 39 nanometers. You might be wondering why use a number 39, why not some other number 50 or 100 or something like that. Okay, let us come to that a little later. Okay, now what we do is conduct an experiment of measuring the electrical conductivity of these two materials. Okay, made up of copper atoms. Both these materials are made up of copper atoms. Both the dimensions are the same, but only thing is inside these materials, the microstructure, the grains are of different sizes. Okay, in one case the grains are very big. That means you can easily see with your eye. You don't even need a microscope to see the grains. You can see the grain boundaries neatly with your eye. So so we are saying that the grains are about 0.5 millimeters, so you can easily see with your eye. And in another case you have nanocrystalline grains, small grains. Okay, each grain is on average is about 39 multiplied by 10 power minus 9 meters. Okay, 10 power minus 9 meters is nothing but 1 billionth of a meter. 1 billionth of a meter. 1 millionth is itself is quite small, but we are talking about 1 billionth of a meter. So 39 divided by 10 power 9. Okay, 10 power 9, that is what the number we are talking about. So these grains are pretty small, very small. And now we are trying to conduct an experiment which is the flow of current in these materials. Okay, so what I do, I drop a potential V, and across this across this across this this bulk material, and try to measure the current. Okay, so in what, with whatever science, with whatever knowledge we know that if we drop a potential V and increase the potential and measure the current, the relation between the current and voltage will be linear. Okay, will be linear. Now I do the same experiment. I drop a potential V and try to measure the current by varying the potential. Okay, now in this case the current will not be linear, will have some peculiar fashion. Okay, now this observation is different. Okay, yeah, but we know for quite some time that all metallic conductors, electrical conductors, obey Ohm's law. Okay, obey Ohm's law. But in this case, Ohm's law is nothing but a proportionality between I and V, as V is increased. Okay, but in this case that proportionality is not followed. This is that, then we say that the Ohm's law is not valid in this case. Okay, Ohm's law is not valid. Why is it not valid? But because it is it against the science? No, it is not against the science. It is because there is a change in dimensions of the grains, and the grain boundaries have changed. The grain size has decreased considerably, therefore the number of grain boundaries have increased, and these are the places, the grain boundaries are the places which dictate the flow of electrons inside the material. Okay, that has changed. Okay, so we correlate the change in the behavior, the current behavior, the flow of current behavior in such a material due to the change in the microstructure. Okay, and this is a specific number here, 39 nanometers, which is nothing but the scattering cross section, or the scattering length of the electron in copper. Okay, if you make grain sizes less than the electrical scattering length, electron scattering length of electrons in copper, okay, you are going to see some exotic, this is not following Ohm's law, but it is an exotic, unseen, unobserved electrical behavior of copper. Okay, this is one example. Okay, with which we can try to use to understand that at nanoscale the science is no more the science we know. It is now a science called nanoscience, and you have to write a new rule. Now in this case the Ohm's law, you cannot use it. You have to change the law. You have to find out yourself based on experiments, or theory, or whatever it takes, and formulate another law, if possible a universal law, if possible a fundamental law, to explain the electrical conductivity, or in bulk nanocrystalline materials. Okay, and the same is applicable in the case of wires too. Okay, if we consider the copper wire, which actually goes, which we use in our household, in electrical connections, it is typically about, the cross section is about 10 millimeters square. Now imagine replacing these wires, okay, with copper nanowires. Of course here it's not 29, it should be 39 nanometers. Okay, 39 nanometers. If I make copper nanowire with a cross sectional area of 39 nanometers square, I am going to see exotic electrical behavior from this copper. Okay, so is there any relation between the mean free path of the electron in copper to the electrical conductivity that we measure? Yes, it is actually the design parameter, and unless we know this, we should not actually venture into making devices out of the nanomaterials. Okay, so if the diameter is not 10 nanometers, or maybe 200 nanometers square, okay, the area of cross section in the case of the copper nanowire, you may still see some exotic behavior, but not exotic electrical behavior. Okay, exotic, if you have the diameter less than or equal to 39 nanometers, only then exotic electrical behavior will be observed in copper. Okay, here is the crux of the problem. If we know the mean free path of electrons in copper, we have a design parameter to extract exotic electrical behavior in case we make a stable copper nanowire, or copper nano dot, or copper nano thin film, or whatever it is. Okay, I want to know from a couple of you, if I'm able to connect with you before going any further, either the faculty, or the participants,
Yes,
because
sir.
this is very important.
We could
Yeah,
easily and clearly understand, sir. And
okay, yeah,
the basics are, this is the first time we are hearing all these basics.
okay,
We are very
fine,
much
fine,
interested, sir.
fine.
Thank you.
Yeah, okay, I'm going ahead then. Yeah, okay. Now let us define what nanomaterial is. Okay, there are four important. This will not be there in any textbook, but unfortunately it is not there. It should be there, but it is not there. There are four parameters which one should know to classify nanomaterials. Okay, if anybody gives you a material and says this is a nanomaterial, you should check whether that material satisfies these four properties simultaneously. Okay, first and foremost is you have to identify any feature in that material. There is no limit on the type of the feature. It can be particle, it can be grain, it can be diameter, it can be any feature. Please identify at least one feature in that given material, and that feature should have dimensions less than 100 nanometers. Okay, why these 100 nanometers? Another question: why many textbooks write 100 nanometers? Why not 200 nanometers? Okay, now these fundamental parameters, what we'll be discussing in the coming slides. For example, the electrical the scattering length of electrons in materials will not be more than 100 nanometers. If we take this is with regards to electrical property. Similarly, the holes, the scattering length of holes, for example, phonons, for example, scattering length of the phonons will be even more less. It is not more. You will see those numbers anyhow. Will not be more than 100 nanometers. So when you talk about optical phenomenon, phonons are important. Photons are important. They have wavelengths. Okay, wavelengths have dimensions in meters, nanometers. So that number is always less than this 100 nanometers. That is why many of the textbooks write this feature has to be less than 100 nanometers. Even magnetic materials, okay, length of the correlation length called magnetic correlation length, which is the core for magnetic interactions, again the number is less than 100 nanometers. So therefore we say, if you identify any feature, at least one feature, at least one, you can identify more than one. Okay, at least one feature whose dimensions are less than 100 nanometers. This feature can be a grain boundary, can be the size of the grain, can be particle. By the way, there is a difference between, you have to go back and check the difference between particle, crystallite and grain. There is a clear cut difference between these three. So it can be any particle size or grain size or crystallite size or the diameter of a wire or the length of something, anything, any feature. Okay, you can consider any feature, but you have to identify that feature. Okay, at least one feature whose dimension falls in the whose dimensions are less than 100 nanometers. Okay, this is one first parameter to be satisfied.
Sir,
Then
you
that
told about
particular material.
one small thing, sir.
Yeah.
You were telling
Yes,
about
please. Yeah.
particle, grain, and crystal. Difference is there.
Yeah. Yeah.
Can you just elaborate on that, sir?
Okay, so particle, it is basically the nomenclature that is important here. When we deal with powders, okay, we should use the nomenclature particle and crystallite. Okay, now particles can be crystalline particles and amorphous particles. Particles, what do particles have? Particles are constituted by crystallites. What are crystallites? Crystallites are the smallest regions in which the atoms are arranged in a orderly manner. Okay, particles are big. Particles can be amorphous or crystalline. And we are talking about, when we talk about crystalline particles, these particles are constituted by small entities called crystallites. Each crystallite is has a specific order. Specific order means the arrangement of atoms in them is in a systematic manner, not randomly arranged. And all of these crystallites put together, we say as a particle. Okay, particle is a bigger in dimension. Then comes the then within the particle you have crystallites, if it is a crystalline particle. If it is an amorphous particles, there is no both the particle, amorphous particle and crystallites, grains, all of them are constituted by either atoms or molecules or ions. Okay, so when we talk about amorphous particle, in that the constituents, whether they are atoms or molecules or ions, are randomly arranged. There is no order in their arrangement. But in the case of crystalline particles, there is an arrangement of neat arrangement, very systematic arrangement of atoms or ions or molecules. These are the constituents. Okay, but within a particle, within a crystalline particle, if you carefully observe under a micrograph, there will be small entities, small volumes of materials. Further, they are called sub constituents, okay, or sub entities or sub volumes of materials. Within each such entity, the atoms are systematically arranged, but in a different manner. Okay, one crystallite will be oriented in one manner, other crystallite will be oriented in another manner, but all of these crystallites are together, they're adjacent to each other, and they constitute a particle. Okay, now that is the difference between particle and crystallite. Both of them are used only in the case of powders. For example, if we take talcum powder, and if I pick one smallest or uh, one representative solid volume from the talcum powder, I call that entity as particle. But in that case, the particle is an amorphous particle, because if I put that particle under a powerful microscope and see how the atoms are arranged, they are randomly arranged. Okay, and at the same time, if I take a powder of iron or copper, and pick one entity and put it under micrograph, and that one entity I call it as a crystalline particle of iron or copper. And within that particle, if I use a powerful microscope and see, there are some sub entities or sub volumes of materials locally within that particle. Each one of them is oriented in a different manner. There can be 20 such entities, and these 20 entities are called as crystallites. Crystallites are smaller entities, but they're still systematically arranged. Within those crystallites also, the atoms are systematically arranged. Okay, then that particle we call it as crystalline iron particle, which is constituted by crystalline iron crystallites. That is the nomenclature. Now then, what is grain? When should we use grain? Okay, now when we let us take grain is related to crystalline materials. Therefore, let us take the same example of the iron powder. Okay, iron powder, uh, and then try to consolidate, make it a piece of iron. Okay, make it into a piece of iron. All the powder particles are now put together, and then a piece of iron has been made. And you put this piece of iron under a microscope and observe, you will see more or less the same arrangement of atoms, within the sub regions of sub volumes. But in the case of the solid iron piece, you no more will use the word crystallite to explain the small volumes, small crystalline volumes within that solid. Okay, in that case, in the case of a solid iron piece, you use the word grain. Okay, that is the difference. They are, but in our textbooks, invariably crystallite is used for grain and grain is used for crystallite. Grain, the word grain should be used only when we are dealing with bulk solid materials, not with powders. When we say powders, we use either particles or crystallites. We don't use the word grain. Am I clear?
Yes, sir. Very much clear. Clear.
Okay. Yeah, let's go to the definition of how to define a nanomaterial. Okay, now if we the second one is, these materials should exhibit novel and superior properties. When I say novel and superior properties, these are unheard of properties. We never measured such properties. We never, as humans, we never observed these properties, and now there is a material which is exhibiting these properties. Okay, that otherwise they are not interesting. Okay, so that is the second point. Of course, you have to make these measurements and prove that these are exotic properties. The third important, if you see, I put that in red color. Okay, all of them, what are the important in the slide, are put in red color. Okay, so length scale less than 100 nanometers, and then novel and superior properties. The third and important point, which is put, all the words are put in red color. Presence of significant fraction of constituents. Presence of significant fraction of constituents. Constituents can be atoms, molecules, ions, whatever, it doesn't matter. Okay, should be at the interface or at the surface. Okay, let me explain this with this example. Okay, this is the schematic of C60 carbon 60 buckyball or fullerene. Okay, so it is constituted, the constituents are carbon atoms, these are carbon atoms, and we are saying C60, there are 60 constituents, 60 carbon atoms, and in order to classify this as nanomaterial, let us apply these, the first rule. Can you identify a feature, at least one feature, that is less than 100 nanometers? So I'll measure the diameter of this ball by using an appropriate technique, and this diameter is 1 nanometer. Okay, 1 nanometer. Okay, this is the real image actually, STM. Okay, this is the real image. Okay, now I will say, now I have identified the diameter of this feature, this material. What we have not named it yet, let us name X material to be 1 nanometer. So this first point is clear. Okay, 1 nanometer is less than 100 nanometers. I have identified the diameter of this material as 1 nanometer, which is less than 100 nanometers. What are the properties? Exotic properties. If I measure electrical properties, I cannot use Ohm's law to explain. Some peculiar, some special electrical behavior, optical behavior, so many properties this is exhibiting. Okay, so that second point is also, it can be used in optical applications, electronic applications, biological applications, whatnot. Then the third point, the second point is clarified. And as I said, all of them have to be simultaneously satisfied. Now, the third and the most important is the presence of significant fraction of constituents at the surface. What are the constituents here? 60 carbon atoms. Significant fraction should be on the surface. What is it? Is like a football. Okay, they're on the surface of a football. You can imagine 60 carbon atoms here, not significant fraction. All of the 60 carbon atoms are on the surface of this feature called buckyball. Okay, called C60. So even the third parameter is satisfied. Then the fourth one, stability. This material, from the time we synthesized till the end of the application, that means the life of let us assume that this C60 is used in a solar cell. Okay, the life of solar cell is, let us say, from say 6 to 7 years. From the moment we synthesize this C60, from its use in a solar cell is made and it is put in application, until the life of the solar cell is over, this particular C60 should be stable, phase wise, crystallinity wise, size wise, everything properties wise, all of it have to show stability. Okay, and only when these four things are satisfied, we call such a material as a nanomaterial. In this case, it is a C60, which is the smallest allotrope of carbon. Okay, C60. And the synthesis of this, the extraction of this, or the preparation of this, has won the Nobel Prize, if some of you know. Okay, two carbon nanomaterials named C60 and graphene have won the Nobel Prize, which such a privilege is not there for any other materials. Okay, uh, uh, so this is very important. So you know that these four have to be there. So it is up to you to design such a material. Okay, and if you want some exotic electrical properties, what is the design parameter? The scattering length of electrons, which we know for quite some time. It is I'll show you in the next slide. Okay, scattering length of charge carriers basically fall in 100 to nanometers. For reference, you can access this paper and elaborately study the scattering length of charge carriers. So for example, copper, the scattering length is 39.9 nanometers. Okay, 39 nanometers. In angstrom units, it is 399 angstrom units. Okay, 399 angstrom units. But it in nanometers, it is 39.9 nanometers. Okay, the scattering cross section or the scattering length of electrons, which is the most important parameter in deciding the electrical conductivity in that particular material. Okay, so if I wish to extract any exotic electrical behavior from copper, I need to make a copper in such a way that in that copper, at least any feature, it can be any feature, it can be the diameter of a copper wire, it can be the diameter of a copper particle, but that feature should have dimensions less than or equal to 39.9. Otherwise, there is no possibility of extracting any exotic electrical behavior. Maybe you can extract some other behavior, but not electrical behavior. Okay, because now the electrons which are there, suppose here you see here, this is a gold particle which is about 15 nanometers. Okay, 50 or maybe 15 to 10 nanometers. If you see gold, the the electron scattering length is 37.7. Okay, here it is the particle itself is 10 nanometers. Okay, the diameter of the particle is 10 nanometers, but the electrons which are there in this so when you have atoms, gold particle means it is made up of gold atoms, and gold atoms are there, electrons are also there along with the nucleus. Now these electrons are, we say, confined. You might have heard this word. Let us not go into that, but this is what is meant by confined. They have to change. They cannot come out of the system because they have to be there inside the system. But in order to be there in the system, they have to adjust their properties, their behavior, in order to be there with the system, the stable system. Okay, that change in behavior of the electrons is reflected as change in exotic as the exotic properties. Okay, so how do you, if I want to make particles, powder particles of copper nanoparticles, the size of these nanoparticles, the purpose is already fixed. We want to extract some exotic electrical behavior. Therefore, I have to make these nanoparticles less than 39.9 nanometers. Otherwise, no exotic electrical behavior. If I want to make gold nanoparticles to extract some electrical behavior, some peculiar, some useful, some variety electrical behavior, the diameter should be less than 37.7 nanometers. Okay, similarly, if we take phonon, if you want to tap some exotic thermal properties, again the size of the nanoparticles should be in the range of the phonon mean free path. And phonon mean free path in for example classical aluminum, gold, and silver, aluminum, silver, and gold, the phonons mean free path is in between 1 to 1 to 10 nanometers. So what it means, if I were to extract some exotic thermal behavior of aluminum nanomaterial, unless I make these nanoparticles less than 10 nanometers, I'm not going to see any exotic thermal transport. Even if it is 20 nanometers, even though people say that it is nanomaterial, you will not get any exotic thermal behavior. You might get some other behavior, but if you want to extract some special thermal behavior, the particle size, or if you want to make aluminum nanowire, the diameter of the aluminum nanowire should be less than 10 nanometers. Otherwise, no exotic thermal behavior, no exotic thermal transport. Why? Because it is related to the phonon mean free path. Phonon mean free path in aluminum is in between 1 to 10 nanometers. Therefore, this phonon mean free path becomes the design parameter. Therefore, it is very difficult to extract thermal properties because it is difficult to make such nanostructures. Okay, so it is very important. Similarly, with the length of exchange interactions in the magnetic materials, if you want to work at, you can there are several physical magnetic phenomenon that can happen in magnetic materials. And all of these can be by virtue of design. You can, if you talk about atomic scale, you can make nucleus and nucleus, nuclear spin and nuclear spin interact through another atom, nearby atom, if you are making these materials at this length scale. You see, if I make nanomaterials, such nanomaterials, copper for example, copper is known to be a non-magnetic material, but if I make copper into nano copper, I can match the dimensions of this nano copper with the length of exchange in copper, and therefore I can even strike some other magnetism, not diamagnetism. I can at least strike paramagnetism, or in some cases, in carbon, for example, people have shown ferromagnetism. Okay, not long range but short range, but this is because of this. They have designed a material in such a way that they could find at least one feature which is less than or equal to the length of exchange interaction in that particular material. Therefore they were able to see exotic magnetic interactions. Okay, so these become even in for mechanical engineering, for example, if you want to design unique high strength materials, okay, again there is a design criteria. Okay, classical materials people are using, but now I want to bring in a novel nano bulk material. I want to make replace steel in construction. Okay, now here is the design criteria. Okay, it is very well known for a long time that creation and movement of dislocation is very difficult in spatially confined regions. What is spatially confined region? If we have two grains in a material, okay, if you have and then surrounded by some amorphous material, okay, suppose I have this is the microstructure. I have two grains, crystalline grains in between this region. Okay, if this is called as spatially confined regions. Okay, so if I have this region, the length of this region, the separation between these two in nanometers, okay, then I can make the dislocations movement and creation very difficult. And the moment you have this, the materials become become high strength materials. Okay, so this is one classical example. Aluminum scandium alloy is made in such a way that the whole matrix is aluminum scandium matrix, but in the matrix they had these small crystalline, you see the white dots, the bright dots in this image. These are aluminum scandium precipitates. They are arranged in such a way, these precipitates are arranged in such a way that the size of these precipitates and the gap between these precipitates, okay, is similar. Okay, so when this happens, the size of the precipitates is about 2 to 4 nanometers, and the distance between any two adjacent such precipitates is again 2 to 4 nanometers. In that case, you have designed a space called spatially confined region. In that region, it is very difficult to generate to create dislocations and also move dislocations. And the moment such a situation is created, this particular material exhibits very high strength, hardness, all the mechanical properties that are needed. Okay, and therefore we say that the preparation and the use in nano of materials in nanotechnology is design based. It's not arbitrary, and this can be tried in several other materials also. It is not just specific to this material, because the science here is if you have a spatially confined space, that is the space between two nano features like this, like precipitates, and the dimension of the space is close to the dimensions of these particles, you are supposed to use you have supposed to have created a space called spatially confined space. And it is well known that if you have a spatially confined space, it is very difficult to create and move dislocations. And when you have a situation where it is difficult to create and move dislocations. That material is said to be having high bulk modulus, and if you have a high bulk modulus, it is or any other modulus, elastic modulus, or these such moduli, you can design the strength of the material by adjusting these the size of these precipitates and also the gap between these precipitates. Am I clear? Yeah, I think I have to close here because I have to again give a talk somewhere else. This was on a short notice, so I could cover only this. Yes, madam. Dr. Padmalata.
It was so nice that we wanted more, sir, because you are giving from basics you are starting, and it was very interesting to hear your lectures, sir. Because such a
Yeah,
basic
I'm
no
glad.
one will cover, because you
Yeah,
are covering from the basics of the subject. We
yeah.
really missing your lectures, sir.
Yeah, maybe some other time, but as I
Yes,
told
yes,
you,
yes.
at 2 o'clock, I have a schedule. I mean, that was
Yes, sir.
planned actually.
Yes,
Yeah.
sir. Yes, sir. We
Some
understand,
other
sir.
time. I mean, whenever you have audience, I'll be open to give
Sure,
a
sir.
talk.
Sure, sir.
Yeah.
We can, for our college, will be inviting you for guest lecture, sir. Because such a
Sure.
beautiful
Sure.
lecture you have given, sir. Because all the concepts, because we know nanomaterials, but the depth of the
Yeah.
subject is very nicely covered, sir.
Yeah, I'm glad. I hope others also have the participants also have connected with the slides
Participants, if
and
you
my
want to share
explanation.
any feedback, dear participants, you can share.
Yes, madam. Thank you. Sir, good afternoon.
Yeah, good afternoon.
Sir, myself Ravi. Sir, a small doubt is whenever we are going to consider the diameter of the nanoparticle, it will affect with different diameters. For example, I am going to take copper oxide.
Yes, yes.
Shall I use like a 20 nanometer or 30
Yes. Yes,
30
yes.
nanometers,
Yeah.
and which will gives the more effective? I mean, whenever
So,
we are going to use for heat transfer case.
yeah. Okay. So for heat transfer, you are only talking about heat transfer. Huh? So
Yes,
thermal behavior,
thermal
right?
behavior.
So thermal, and your what is that material you said? Copper. Huh?
You can take copper oxide.
Okay. So what you have to, your first goal should be to find out the phonon mean free path in copper oxide.
Sure.
In bulk copper oxide.
Okay.
Okay, so that number you will get, that can be done through some experiments. I don't know the specific experiment, but you can extract, you can read this paper how to measure the phonon mean free path. Okay.
Okay.
So you have to measure. You may not directly, maybe that is already available in the literature. You can check. Okay, in the databases. You have to first collect the phonon mean free path in copper oxide. In bulk copper oxide, that number will be some number 20 nanometers or 10 nanometers depending on what it is. Okay, then that becomes your design parameter. You should not make nanoparticles above that material, otherwise no thermal transport, no exotic thermal transport.
Okay. And some
Let us say in copper oxide, let us say in copper oxide it is the mean free path is 20 nanometers. Okay, so you have to make a copper oxide nanoparticles less than 20 nanometers, not above 20 nanometers for thermal transport. That is the understanding.
And the some literature are saying that the thermal conductivity enhancement should be more than 10 times of base fluid.
Yeah.
Is it possible?
Yes, you can, but it all depends on the stability and other things. No dispersion. See, you might put it on a paper on a software, but in reality, these nanoparticles agglomerate because of the whatever interactions they have, and they become a bigger particle. No, so dispersion, mono dispersion is very difficult. Okay, so you have to also find out surfactants and other things to have a mono dispersion. And once mono dispersion is there, you can have manifold effects. Yeah.
Okay. And while you are going to do the research, shall we can use like different nano materials with different diameters?
Yes, of course you can use.
Okay.
Of course, but you should be always less than the critical parameter. The diameter should be always be less than the critical parameter for whatever property you're aiming at.
Okay. So for
Yeah.
example, I am going to use base fluid as water. So for the water,
Okay.
there is no diameter or something else.
No, not water, not water.
Sir.
What is the material you are going to disperse in water?
For example, copper oxide, you are taking.
Okay, so first thing is find out the mean free path of, that is the fundamental parameter. Okay, find out the mean free path of copper oxide. Phonon mean free path in copper oxide.
Okay.
You will get some number, right?
Yeah.
That number is, let us say, 20 nanometers. Okay. You can make copper oxide nanoparticles 5 nanometers, 10 nanometers, 50 nanometers, 20 nanometers, but not 25 nanometers.
Yeah.
Okay. See, in the 5, 10, 15, 20, you might see exotic behavior, but not in 25, as far as thermal behavior is concerned.
Okay.
Yeah.
Good. Thanks.
Madam, I'm sorry, I have to quickly, I mean, I have to make some preparation.
No problem. Sir, thank you, sir. Thank you. You have come and presented for us.
Yeah.
Such a nice presentation.
Yeah.
Thank you very much.
Thank you.
Yeah,
Sir.
Thank you.
I'm glad to let. Yeah, I will hope we'll meet again soon.
Yes, sir, surely we have to meet.
Yeah.
Thank you, sir. Thank you for accepting.
Thank you, Venkatesh. Yeah. See you soon.
Right.
Yeah.